Welcome everyone again. Thanks for joining. It's great to see all of you here. As a lot of you know and are probably experiencing, January has been an interesting month for a lot of us. There have been 3 teachers who were going to present experiments who had to cancel either because of COVID or because of political demonstrations in their country. So I really appreciate those of you who can still come here and make the effort despite everything going on in the world around us. As a lot of you probably know, I ended up needing to delay the date of this month's experiment share by a week because I was stuck in Canada with COVID myself. So it's been a rocky start to the year, but we've got a great lineup of experiments from the USA, Greece, Serbia, UK, Brazil, Italy, Ireland, and me here in France. Having mentioned COVID, that's an excellent lead-in to Stuart in California, who's going to be showing us part 2 of his forget the name of it, like vaccines and COVID, like the disease spreading related experiments. So Stuart, it's great to have you back for the second part of this. Welcome back. I'm excited to have you share the next part of this.
Well, thanks, Michael, for putting this together. It's really awesome. So if you were here last time, I shared a little bit on the vaccine unit that I've put together. It's designed for students in grades kindergarten through 6th, but I think that the activities are very transferable to higher grades. At each lesson has a hands-on activity and then lots of resources that go with it, and you can find all of those. I'm going to put it in the chat right now, haywardscience.com. The last 2 activities, the first 2 lessons, introduced to students what exactly is COVID-19, how it spreads. We did a little experiment on how masks can prevent the spread of COVID-19. Then the next activity was to help students understand how exactly vaccines work, with a little model about that. So the next obvious part of the lesson is to talk about how we know vaccines are effective at preventing the spread of the coronavirus. To do that, I'm using another model. In this model, there's a bunch of these kind of weirdly distorted people that we've made this is an unvaccinated person, and they have a pretty large head, which is also kind of a target. And we're going to be kind of spreading some little quinoa around groups of these people, and depending on where they land, something happens to them. I have 2 versions of these, and one in which the worst thing that can happen is death. I used that with my students, but everybody knows their own students, and for that might be especially triggering for some. So we also have this version that says in the hospital or worse. Next version is feels very sick, and the worst version it says hospital, feels sick, no symptoms but can get others sick, which is an important thing to explain. That a big part of what we know happens with COVID-19 is that people can not feel bad at all and then go to a movie theater and get everybody else sick through breathing. And then if it doesn't land on them, they're not affected. So I'm going to switch over to my other camera, Michael, if you don't mind spotlighting that one.
Sorry, it's just taking me a second to find. Okay, yeah. Here we go. Perfect. Wonderful.
Thank you. And I'll stop that share so it's smaller for people. So what I have here is a big group of unvaccinated folks. And then this is a 1/4 teaspoon of quinoa. And basically what I'm going to do is I'm going to have somebody go into this, I don't know, you call it a classroom of unvaccinated people, and they're going to cough all over them. And that coronavirus, which is represented by the quinoa, gets spread all around. And then on the back side of this same worksheet, I have a little data table for kids to fill out. And so what you do is you come over to this person and you say, what happened to that person? And there is some quinoa on this gray part that says feel sick. So I just fill in for that person. Each of them has a number, feel sick. And then this person number 2, there is one that there's some quinoa that landed kind of all over this person. So in every kind of layer. So what I say is this person doesn't both die. I'm using the one that has death on it right now. Doesn't both have death and has no symptoms, but can get others sick. I just go to the one that is the worst of the situations. So that person has sadly died. And then, you know, person number 3 is in the hospital, and person number 4 has died as well, quite sadly. I won't do these all right now for time. So here is one that I had done just prior. This is kind of typical. I did this just prior to joining. And, you know, what you can see is that there's a lot of people who got very sick. And the other really important thing to notice, and this is one of the reasons why we set up this experiment, is that not everybody got sick, right? Just because you are vaccinated not vaccinated doesn't mean you're guaranteed to get sick. So, you know, this person here didn't get infected at all. And, you know, we're trying to communicate something about likelihood here, chance, and that you're much more likely to get sick if you're vaccinated. That becomes a little bit more clear for the second part of this activity. For that, I'm gonna get my quinoa back. I recommend you do this on cafeteria trays if you have them at school. I don't have any at home here. But for the second part of this experiment, here are my unvaccinated folks. And, you know, you can have students already maybe predicting what is going to happen to this group of people who have smaller heads and smaller targets. For my younger kids, I clarify that you don't have a smaller head just because you're vaccinated. This is a model. And, you know, I'll do this again and cough in this room of unvaccinated people to see what happens. And, you know, right away, you can hopefully start to see a difference. This person 1 did not get infected at all. This person 2, oops, I moved the paper, which you should try not to do. Now he is not infected. I'll say that before I moved it, he had no symptoms. Person number 3 did not get infected. Person number 4 had no symptoms, but was infected, and so on. This is the data I got just prior to this meeting, and we can see a pretty big difference. Lots of people are not getting sick, or if they do get sick, they are getting less sick. They are, you know, not going to the hospital as much. They're not dying as much. And, you know, the important part is to have students compare these two and look at the stark difference that happens. And, you know, it's a really big piece of misinformation that people have when they learn that somebody is vaccinated and they die, and they think, oh, well, that means it doesn't matter to get vaccinated. But that, of course, is not true, because you're much less likely to get as sick if you're vaccinated. So that is that activity. I'm going to very, very, very quickly go to the last activity of my unit, which teaches a little bit about the social responsibility of getting vaccinated, because it doesn't just protect a single individual. Oops. It protects many individuals. And my set of dominoes fell over as I was showing this, which is apt, because what I'm modeling right here is, you know, the spread of COVID, and a person who is upright is healthy. A person who is knocked down has been infected with COVID-19 and got sick. Oops. Sorry, guys. Let me just readjust my camera. So what I'm not doing a great job showing right now, because my camera is falling all over. That's what happens when I use an iPhone. is, so, you have students start by just playing around with dominoes, and they realize pretty quickly that if one domino knocks over, that knocks over the next domino. One person who's sick can knock over the next person who's sick. But what happens when we start to vaccinate people? And I vaccinated these individuals by putting them down on tape. Well, what you'll see is that if this person who is sick knocks into this person, maybe that person gets a little sick, they wobble a little bit, but they don't spread COVID-19 as much. And so that sickness does not spread to the next person, which doesn't spread to the next person, which doesn't spread to the next person. And so you're keeping everybody along healthy, which is especially important if you're talking, when you think about, there are people who cannot get vaccinated, person with cancer or autoimmune disease, people who are allergic to the vaccine, children under 5 in the United States, they would be easily knocked over. If they were exposed to somebody who was sick, they would easily get sick. But if you surround these people with other people who are vaccinated, because everybody in your group got vaccinated, and I, knocked this over, well, that didn't knock over my unvaccinated person. And same if I go from the other side. So much more easy to get to stay safe. All right, so we can undo that spotlight now. That was the activity. And I just want to thank everybody for giving the time. In Hayward, my district that I teach in, just had to, I'm sorry for the motion sickness, everybody. Zoom, I love teaching on Zoom. So my district just had to shut down because of COVID-19 cases. It's as real now as ever. So highly encourage people to teach about vaccines, whether you use my activities or not. And I'll put my website that you can use back in the chat. And Michael has that link with all the materials you need on there. So thank you, everybody.
That was awesome. Thank you, Stuart. And for the links as well, in addition to his overall link, he also gave a couple of links to each activity separately if you want to navigate through those. So those are in the experiment list, which I shared a link for in the chat. And I'll also be sending that out probably early next week when I send out a link to the recording, once I find time to upload it. So that'll be great. I know I'll be trying to do a couple of those with my classes. I haven't gotten around to them yet because it's been busy and classes have only been open a little bit since I've been back. But hopefully some of you guys will be trying those out too. Are there any questions for Stuart before we move on to Astrinos in Greece? And one question that came up after last time, and I think it was emailed to me, so I didn't have a time to ask you, Stuart, was if you have any advice for how to fit it within a science curriculum. Like, because not all programs have something on pandemics or whatnot. And I'm personally of the opinion it's worth making things relevant to the world around them and fitting it into wherever you can fit within a program. But some teachers who might be less used to trying to fit things in where you can might benefit from advice like, when do you decide to teach it in your classes, for example?
Totally. Well, so I think it fits in well, the parts on the immune system fit in well to like an introductory cell biology unit, because you are talking about these different cells which have these different roles. There's a lot of just nature of science work that every single science curriculum hopefully has made time for. So we're actively developing a lesson to follow up on Omicron. And a lot of that lesson is about how the nature of science is that we change our advice, what we do based off of new evidence. So that's another kind of place that you can put it in. I mean, you can always kind of like, I don't know, for me, I feel like I can always figure some way out that with dominoes, you have some physics to add in, right? But I think that, yeah, it depends. Maybe I would love to talk to that individual teacher about how we could brainstorm how to make it work, because I think that there's plenty of opportunity for that. Yeah, I don't know if that was helpful.
I think it was really helpful, and mentioning to talking to that teacher, like if there are teachers who contact me with like that, are you okay with me forwarding your email to them so they can drop you on?
Please do. Like I said last time I did this, I'm currently just completely immersed in this, and I want as many people to be teaching about vaccines as possible because it does have a really positive impact. So yeah, and if you want me to come and chat, do a Zoom with your like science team at your school, I'd be happy to do that. Anything that you need.
Oh, that's awesome. Thank you. And now we're going to head over to Crete in Greece to see Astrinos, who's joining us again. He's been here for every one of the experiment shares and even let me host the first one from his lab. So it's great to see you again. And we're going to see your motorless vacuum cleaner. Welcome back, and thank you again, Astrinos.
Thank you, Michael, for the invitation. I'm very happy to be here with you tonight. This is a very simple experiment. It's actually just only a piece of plastic tube that is used by electricians for insulation. It's I think it has the smallest diameter of something like 11 millimeters. But I have used wider, I think. So what I'm going to do is I'm going to revolve the one end as fast as possible, while the other will be because of well, as it revolves, we have an increase in the airspeed, so it is followed by a decrease in pressure. So we actually create a vacuum that will suck the pieces of paper inside this tube, and well, I hope that you can see. Well, okay. So one will be revolving like this, and the other will as you can see, it does a very good job. Well, they come from the other end, but so everything is, but well, I don't know if you could see that, but they were just coming out from the revolving end. And if some of them are still there, so if I don't know, was it clear, Michael, what was happening?
For me, it was very clear, yeah. Is there anyone who didn't seem clear for?
I can. Well, they get inside here and they go out from the other end.
And I'm just wondering, because it's out of the view of the camera, but when they go out of the other end, do they just fly off anywhere around the lab?
Yes.
Beautiful.
Well, you can actually see that, there are some on my, well, I think that they are all over me, but I can do it again. I don't know if you see, that is why vacuum cleaners need a bag to collect everything.
That's beautiful. And I see a couple of comments and questions coming up in the chat. I'll relay them to you. One is Paul's asking what length of tube you're using and if there's a limit to the length. And along those lines, David's saying you can do it with a whirly tube. And I don't know if you know whirly. Oh, he's pulled one up so we can see. I don't know if they have them in Greece. In France, I think they have them, but they're a lot more expensive than buying piping from the shop. So anytime I want to use one to show resonance, I just buy like a 10-meter section of piping and cut it to whatever lengths I want and tune it that way.
I think there must be a limit in muscle strength, because you cannot rotate it if it is 10 meters to make it. Okay. This is the sound of something that turns. I don't know, but it's quite fast. So if it is, if you have a very long tube, you have to rotate it really fast, and you cannot rotate this length fast enough. You have to do something like this. Oh, well, I think you will not find, but well, I don't know if it's more efficient this way. This tube was as long as the shop could give me for free. It is 1.5 meters.
That's a great unit of measure, the length that they can give me for free.
Yes.
And there's a question as well from Caroline, if you use it to teach about pressure.
Yes, yes. To teach about the Bernoulli's law, and of course we have a lot of different ways, but this is the cheapest and I think the simplest way.
Okay, perfect. Are there any other questions for Astrinos before we move on to Gordana in Serbia? Okay, and I don't think there are, so thank you again, Astrinos. And now I'll turn things over to Gordana in Serbia, who's going to show anamorphic pictures. And I had the pleasure of actually seeing that from her in person in Serbia back in December. So it's great to see you again, Gordana, and great that you'll be sharing this.
Okay, thank you, Michael, and thank you to all of your friends. They're really great, and I always have some new amazing things to learn from all of you. Thank you. Now I'm going to show you some very simple demonstration, which can be used like introduction for optics, you know, for mirrors, for lenses, and the other. We call here this demonstration turning the world inside out. But why? We are going to use just simply, you can buy it at China shop. It's a mirror spray for New Year's decoration, you know, mirror spray. And the other is one empty box, cylindrical empty box. And I made something like this. Here I have a mirror over this cylindrical box. And now here I have one free, it's a free program, small software application. You see this picture. Okay. We can use it like this. But can you see? I hope it's visible.
Yeah, that's coming through clear, yes.
Okay. And I have here some pictures. It's like it's very much. Yeah. Another one. I think I sent a link for this program. It's good for all formats, JP, JPEG, how do you call it, BMP or another.
Yeah, like in any image formats. And that that link, if anyone's looking for it, should be in the list of experiments that you guys have the link to. And you'll be getting by email again.
Yes. And also kids can bring their own pictures. They like it very much. Their own selfies. And this is Nikola Tesla. Have a good day. That's all.
That's excellent. Thank you, Gordana.
Thank you, Michael, and thank you all.
And Paul had mentioned that that's a really good mirror from the spray. I've never actually used it before, but I'm eager to get my hands on it. And if it's useful for anyone else, like I know in France, that's what I'm more used to because I live here, you can buy mirror board from the hardware store. I haven't known to look for mirror spray, so I'm going to look for it next because I think that'll be even better. But mirror board is like flexible, like cardboard with a mirror surface that could work for that as well. Are there any other, or are there any questions for Gordana before we move on to David Featonby in the UK? Oh, there's a question what the name of the software that was used.
We put it in our timetable. Here we have description.
So in the list of experiments, well, and actually now that I'm double checking it, there's a YouTube video there, and there's probably a link in the description of the YouTube video.
Yes, video, yeah.
And like afterwards, I'll go back and I'll find the link to the program itself from the description. And I'll add it to the document, so you don't need to go through that. Okay. Are there any other questions? I think that's it. So now we're going to turn things over to David. And do you want to introduce what happens next before I cue up the video?
Oh, well, it's just a few. I'm just good. Are you there? Am I there?
Yeah. I spotted you because I saw you put on the wonderful hat. So it's worth showing that.
I hope you know that I'm singing from England. Anyway, we're going to do balloons today. And I've got a video that I'm going to show you of several little experiments with balloons. I finished this and then I thought of 6 more. So anyway, here's if Michael can clip on the video and you'll see 3 minutes of balloons. Might have noticed you can rub a nice little game is to see how many balloons you can stick on somebody as a competition. But you can see it's electrostatically charged and stuck to my hand there. So that's a good thing to do. Talking about electrostatics, I find that these modeling balloons are really good to exciting. Charge them up. Give them a charge on your hair if you've got any. And of course your hair's standing on end now. But you can stick them to anything very easily, much more easily than the large balloons. Now another nice little experiment I like to do with these water bomb balloons is there's the bed of nails. Here's a bed of drawing pins. You press the balloon on the set of drawing pins, it doesn't burst. But if you have an individual drawing pin, oops, bang, there you go. So that's something else you can do with these balloons. If you actually demonstrate them by sticking them on your head, always remember to take them off if you're trying to do a serious lecture like I am. Now, one of my favorite experiments with balloons is the 2-balloon experiment. I have a large balloon and the 6 identical balloon, but just blown up a very small amount. And the question is, what happens when you release the valve in between? Will the big one blow the little one up, or will the little one blow the big one up? And the pressure is such, and in the 2 balloons, it's much bigger in this one than it is in this one. The pressure's higher in the small balloon than the big one. So when you open that tap, the little one, you see, blows the big one up. And that's quite amazing for some people. Now you can do that, illustrate that in another way with 2 balloons to a Y piece, an X piece, or whatever you call it, piece. And if we blow the balloons, you can't blow balloons up at the same time, because as soon as the pressure is different in one, the lower pressure will blow up first. The balloon pressure starts high and then goes low as you blow them up. It's not a straightforward Boyle's law type of thing. It's got the factor that you're increasing the amount of air at the same time. Here we go. Only one of them will blow up, I predict. Ready, steady. Oh, there's a leak in this balloon. That's a bit of a disaster, isn't it? Let's put another balloon on. I was going to say the blue one blows up or the yellow one blows up, so let's try again. See, so only one will blow up the balloon, no matter how hard I blow, till you get to the very end and about to burst the balloon. Only one will blow up. That's balloons. Another type of balloon is the Kamafuse balloon, which is a Japanese paper balloon. The clever thing about that is it doesn't go down the hole there, and it just stays up because there's no elasticity in the paper of the balloon. And the other clever thing about these is if it gets a bit squashed like that, in order to blow it up, you just push it round a bit, and bashing it round, oops, bashing it round enough like that, and the balloon is blown up. So that's Kamafuse balloons. All of these, I think I've done everything. Now that I was in, oh no, there's another game you can play with your students, is to see how many balloons, how many cups, paper cups or plastic cups, your balloon will be able to hold. This is again about pressure. Just start it, put the balloon in there, and the cup stays on the balloon, but how many can you stick on? Because you can put another one on here. That one stays on. 3, another one. 3, and so on and so forth. So you can have a competition with that. As the balloon get less into the cup, the pressure will get less, and so the cup sticks on. There's a few little experiments with balloons. I hope you enjoyed playing with them, and we'll see you next time. Next time, I'll do another set with bubbles. That's even more exciting. Bye for now.
Good. That's beautiful. Thank you, David. And for those of you who don't already know about David's series, What Happens Next, he's got a great series of videos and 2 webinars coming up next week. I'll put a link in the chat. So if you're interested in that, people can still sign up now, right? Sign up is still, registration is still open.
Yeah.
And on Tuesday is for primary, on Wednesday is for secondary teachers, I believe.
That's right.
And if I'm not mistaken, but it'll say in the link and you'll know for sure, but I think it's 5 o'clock for each of those, right?
5 o'clock your time, 4 o'clock my time.
Oh, right. So I know I'll be there, and I hope everyone else will join David as well, because he's always got a lot of wonderful things to share. So thank you for all those great balloon experiments. So now I'll get back to Jeane de Fatima's experiment from Brazil. So as I was saying, I've just queued things up to read her text. So I'm going to be reading a short text from her, and then switching to a video that she sent where there's some text in Portuguese. Hopefully some of you might be able to understand that. But here we go. What is cold? The teacher asked his student. He got up, walked around the room, looked around and replied, cold is the absence of heat. The professor, surprised by the answer, who was also observing his surroundings and impressed with the answer of the boy who was only 10 years old. Who is this boy? Einstein. Magali will introduce us to the empty cup experiment. When placed in the freezer, it retains the cold and even has a translucent appearance. Over time, what happens? Watch this beautiful experiment. And so we'll see 2 short videos that have been sent of Magali, a young student in Brazil, with this cup freshly out of the freezer. And a second video of further observations.
Jeane, já terminou para mim.
Terminou para você? Então deixa eu ver. Vamos lá. Tá aí? Então, peraí. Então deixa eu escrever aqui. Magali já terminou. Tudo bem.
Okay, and Jeane, in Brazil, do you have anything to add, or does anyone have any questions on what we observed on the glass coming out of the freezer there? Okay, and I think that's it for that one. So thank you for sharing that experiment. Now we're going to be going to Italy, where we'll be seeing Giulia sharing another experiment. It's great to have you back, Giulia. A lot of you might remember her previous one on the Motorless tank, showing ocean currents, modeling what was happening in the Bosphorus Strait, or anything with a difference in concentration, or it's like salt concentration or temperature. So we're going to see another marine science one. Great to have you back for another experiment, Giulia.
It's a pleasure. I love the sea, and this activity is about the sea. It is about ocean acidification due to the increase of CO2 in the atmosphere. The increase has been particularly relevant since the beginning of the industrial era, and about 1/3 of atmospheric CO2 dissolves in sea, but it comes with at a cost, because dissolving CO2 makes seawater acidic. Now we are going to simulate the acidification of seawater and the effect on marine organisms which have some parts of their body made of calcium carbonate, calcifying organisms. The needed material are very few. We need only some distilled water, the type used for ironing, not a specific lab equipment, a small bottle, and universal pH indicator with a color scale, and some material made of calcium carbonate. It could be eggshells, today I ate eggs, or it could be marble, or seashells like this. All of these are made of calcium carbonate, but they need to be crushed, finely crushed, to react quickly. So you can crush with the hammer. This is marble powder, eggshell powder, and seashell powder. I use seashell powder to simulate the action of CO2 dissolved in seawater on marine calcifying organisms. So let's begin. I have this small drink bottle with distilled water, where I add some drops of universal pH indicator. Until I have a clear coloring of the water. You can see the color is green. That means that pH is about 7. It is a bit more blue than green. Let's try with another bottle. This is distilled water again. I am afraid the other bottle was something wrong. Universal pH indicator. Let's check the color. Oh, that's much better. The color is as expected. This is a wrong bottle. The other one was a wrong bottle. This is the right one. You can see a greenish color. I add some more indicator to have better sight on the pH color. Green means pH 7. Then I blow gently into the water. As you can see, the color is changed from green to yellow. Yellow means pH about 6. So this water has been acidified by means of my breath. What would be the effect of marine calcifying organisms? I can add some seashell powder. I prepared myself with the hammer, crushing the seashells collected on the shore. If you don't have seashells, you can use eggshells. It will be the same. Let's have a look at what happens now. Oh, the color has changed. That it means that a chemical reaction has happened. And the chemical reaction means that the color has become green again. Green means neutral pH. So the reaction has happened between acidified water and calcium carbonate. Calcium carbonate like in seashells. Remember, if you don't have crushed seashells, the reaction will be slower, requiring 1 or more days. But the change in color is dramatic enough if you have crushed material, or seashells, or eggshells if you live far from the sea, or marble powder. That's all. Thank you. I'm sharing now the links to the activity and to the presentation with other activities about ocean acidification. Many thanks.
That's excellent. Thank you for another great sea experiment. Are there any questions for Giulia before we move on to Paul in Ireland? Oh, and a good question. Would this work with mussel shells?
Of course, if you crush it in a fine powder, you'll obtain the same result, because mussels, clam shells are made of calcium carbonate. So the reaction is exactly the same.
And presumably, if you wanted to or had to, you could use bones or teeth, although that wouldn't be as direct modeling the sea, but they'd also be carbonate, so it should work identically, right?
No, not really, because bones and teeth are made of another calcium salt that is phosphate. Is another kind of calcium carbonate you can find in seashells. If you don't have seashells, you have eggshells. Easy to find anywhere. Or you find a piece of marble and you can crush it with a hammer and you obtain a powder of calcium carbonate or any carbonate rock if you have in your region.
And even chalk, if your school still uses chalkboards rather than having moved on to whiteboards with markers, if it's real chalk, that's always a good go-to source of easy to powder carbonate.
You can have your students explore where this effect is more relevant in tropical seas or in northern southern seas, I mean polar seas, hot water or cold water. Let's try this question with your students so they can explore that the phenomenon is more relevant in high latitude seas due to major solubility of CO2 in water.
That's excellent and somewhat counterintuitive when, like, a lot of students would say hotter reactions go quicker, it should be that, but they don't necessarily think about the solubility of carbonate.
Of course, but the changing color is a sign of chemical reaction. And the chemical species that you have here are only water and calcium carbonate, apart the pH indicator that is for the color.
Excellent. Are there any other questions for Giulia in Italy before we switch over to Paul? And I don't think there's anything else. So let's switch over to Paul. It's great to have you back, Paul. I'm looking forward to seeing what you're going to share today.
Great. Thank you, Michael, and thank you, Giulia. That's a really tough experiment for me to follow. I really liked it. I loved how simple it was, but yet so important and so wide that it can actually lead on to further investigations. So hello, everybody from Ireland in Dublin. I'm delighted to be joining you again and seeing all these amazing experiments. I'm writing down furiously, and I'm really looking forward to seeing the video so I can recreate these experiments. Thank you, Michael, for putting us together from all parts of the world. You really are a powerful person, okay? I'm not going to show too many things because I want to see what you've got as well to show us, Michael. You know, you're very good hosting us, but I think you've got some nice experiments as well. My first experiment, I'm just going to swap over to another camera. This is an interesting experiment that you can do with your students. I have here a tube with 3 tennis balls. Ask your students, which is the greater distance from the bottom of the tube to the top, or the distance going around the rim? Many students, I think, will suggest that the height of this tube is bigger than the rim. I'm going to take off the label, but we will use it in a little while. And we are going to measure the height of the tube. Okay, it's that distance there. And if I bring it around and compare it with the rim, you can see that the rim is much longer. I can do this also with my hand. I can just about reach the top and the bottom with my hand extended. But if I grasp the rim, then I can't go fully round. And now for a little bit of mathematics. Let's say that each ball has a diameter of d. Let's just call it d. I don't know what it is, but let's say it's d. So that's 1d, 2d, 3d. So the height of the tube is 3 diameters. Now the distance from here across to the other side is also a diameter, but the circumference is 3.14 times the diameter. And so mathematically, the rim length is bigger than the height of the tube. Do you remember the label that I took off? It went around this distance and just about closed. If we are right in our thinking and we line it up, you can see that the label is actually longer than the height of the tube. Now, this phenomenon, an optical illusion, happens with many cylinders. It may be because we're not very good at judging curves. This is another cylinder where you can try out the experiment. You can see that is the height. Okay, but yet there's the rim. I hope you have enjoyed this experiment. So that's something for you to try with your students. I've got at least one more for you, but I am conscious that I want to pass over to Michael. Okay, but I want to show you this because I think it's a bit of fun. Okay, what I've got is I've got a sheet of glass. Okay, it's from an old gold leaf electroscope, but it doesn't have to be from that. A piece of glass, or this can often work with a plate. And Michael, you mentioned there earlier whiteboard markers. So this is an experiment to do with whiteboard markers. Okay.
Oh, I think I know where you're going with this one. I like this.
Yes, anyone who does this has to do it with a man. I think that's the thing. Everyone does it with a man. Okay, so these are just two different color markers. Okay, and these are whiteboard markers. They're not permanent, and the chemical that's involved is a silicone, which is actually insoluble. And if the gods of science are with us, these two men may start to float and move around, or at least distort. There you go, that fellow's distorting. So I did this with my students very recently, and they had great fun. You can see they can dissolve and they can do little dances, okay? And they can actually disappear. Some marker pens are better than others, okay? But the actual ink is being forced to the top of the liquid, okay? And so floats along Okay, the red is working better for me today. Okay, you can try this with a plate or a white bowl. Okay, and I can get very destructive in a moment, and my men will disappear. Okay, so that's a chemistry experiment. Michael, I'm passing back to you because I want to see what you've got. Thank you, everybody.
Okay, that's great. Thank you, Paul. And the I'm just looking for how to unspotlight you. Okay. And the last time I did that one with the whiteboard marker, it was actually when I was in Serbia in December, and I wanted to do a chromatography, and I had asked for washable markers. And my friend, a teacher there, he gave me a bunch of whiteboard markers and said, "Oh, these should be water soluble." And I said, "No. We'll show another experiment with this to show you that they're absolutely not water soluble." But now we'll finish off with me showing a short experiment on pressure. So all I'm going to use is a resealable, like, sandwich type bag and a drinking straw. And I'm going to use the straw to blow up the bag. This one has a hole, so it's good I have a spare. And just with the pressure from my breath, I'm going to be lifting a couple of textbooks. And you'll see that I use textbooks sometimes in my teaching, but usually only as a source of mass or like a dead weight. Okay, here we go. This bag doesn't have a hole. So I'm going to use a chemistry textbook. I'm just going to place the bag under the textbook, and just with the force of my breath, it's easy to lift up the book. Now, so far, there's nothing too impressive with that. But pressure is proportional to the area involved and inversely proportional to the force. So if I use a bag 5 times the area, then I should be able to lift 5 times the mass. So I'm going to take a small stack of textbooks, and I'm going to try and lift this stack of textbooks up just with my breath. They slide around a little bit, but it's not that hard to lift them up. But where this gets interesting is then if you scale it up, and I'm alone right now, I don't have a class full of kids to act as volunteers, but if with my breath I can lift 5 kilos, then if we scale that up and we have 10 kids, then 10 kids together should be able to lift 50 kilos. Or 20 kids, they should be able to lift 100 kilos with their breath. So I'm going to share my screen again and just show you one example. And I do this with kids all over, like in my own school in Paris, but this is a number of kids in Ghana where I'll be returning at the end of February. And that's why I wanted to show this experiment. It's a fun one where you can involve calculations for pressure, but here we have, I think it's 6 kids, maybe 7, lifting up one of their classmates on a desk that's turned upside down on bags that are barely bigger than my small one. They have little bags for water there because you can't drink tap water. So it's a good one to finish up with a crowd where you can give everyone a bag of water, see how fast they can drink it, and lift up one of their classmates. And if you want to involve a little bit of actual like calculations in physics to this, I'm just going to stop sharing my screen for a sec. Then you could, and I'm only going to skip through it verbally. If anyone's interested, send me an email. I'll send you the numbers more. But this bag is 10 by 14 centimeters. So its area is 140 square centimeters. Lifting a book that weighs 900 grams and has a mass, the mass is 900 grams. The weight is just shy of 1 Newton. Then calculating it out, we get just under 1 kilopascal of pressure is required to lift it up. We scale it up and have 50 Newtons. We still, with that 1 kilopascal force, work out that we can lift it up that way. And I wanted to share this as the last experiment because I also want to share announcements about the next upcoming experiment shares. So the next one, tentatively and hopefully, is going to be on Wednesday, the 16th of February. those of you who have joined me for this one and for December's one will know that I needed to change the dates of both ones because of COVID-related mishaps and a little bit of uncertainty. So I haven't yet committed or sent out a sign-up form for the 16th of February, but I'm hoping it'll go through then. But also, I'll be returning to Ghana, West Africa, where I go every year or sometimes twice a year if travel's easier, to give workshops for teachers and work on resource centers. And I'd like to invite anyone who wants to try and share experiments with me there. I'm going to attempt to have some kind of like extended version of experiment shares where it'll be like I can be your eyes, your ears, and especially your hands for recreating some of your experiments there, either for workshops I'll be running for teachers or just at some of the work, the resource centers I work with there to try and put equipment in instruction sheets. It's a little bit ill-defined, my schedule there for the moment, so I'll be sending out more information later. But anyone who wants to participate in that, just drop me a line to let me know if you'd be interested in probably like a 20-minute or half-hour session where you'd be going into a bit more detail to explain to teachers there, and I'd be having them actually recreate it live rather than just watching with you. But that's an experiment share related thing coming up at the end of February, beginning of March. If I don't need to delay my trip again, like last year, I planned on going in February and delayed till April. Might happen again. Who knows what the pandemic will be like. But if that doesn't happen, I'll be there the 18th of February to the 6th of March, and I'll try and set up a couple of different things to involve anyone who wants to join via Zoom to help share things down there. Then I had an idea just as Paul was showing his experiment, because it reminded me of a number of experiments that I do to celebrate Pi Day in March. I don't know how many of you are familiar with Pi Day, presumably a lot of you, but not everyone. But it started at the Exploratorium in San Francisco in the late 80s, where they celebrate the 14th of March with a bunch of Pi-related activities. And it could be good to have the March experiment share, to have a Pi Day special and have everyone try and share Pi-related experiments. So that might be coming up on the schedule as well. Does anyone else have announcements they want to share with everyone before I conclude and say goodbye to everyone? Doesn't sound like anyone else has announcements. And one request or favor just before we close, can anyone who's not shy and doesn't have the camera on already turn on the camera just to take a picture, to have like a picture of everyone who was here? If you're shy and don't feel like having a camera on, don't worry, like you don't have to. But we'll just give it 5 or 10 more seconds for everyone else who feels like turning the camera on to be part of the group picture. Oh, and to give it about 5 more seconds, just another announcement. A lot of you are already familiar with it, but I have a similar project for students rather than teachers, similar to the experiment share. I call Yes International. And there we have meetings where each of the Zoom sessions, there's one school who's presenting experiments. But if anyone has a science club or students would be interested, drop me a line, and we're always looking for more students and clubs to join that. Okay, I'm just going to take a couple of pictures of everyone who's here. You're all looking beautiful. Thank you for joining. So with that, that concludes this experiment share. Thank you to everyone for joining us again, and thank you especially to everyone who presented experiments. Even though Paul was eager to see my experiments, I know from experience when it's just me sharing, there's not nearly as much excitement. It's not nearly as interesting for me as getting to see what you guys share. So thank you very much, everyone, again. Have a great evening, everyone. Or if you're somewhere where it's not evening, have a great whatever part of the day. Thank you, everyone, again, and goodbye.